Hi everyone, I'm out today, so I recorded a little video for our notes. I want you to start by reviewing graphing this quadratic with transformations. So pause the video, graph it, and then press play to get the answers. Okay, here's our answer. Here are my parent points. To the x's we are adding 2, and to the y's we are multiplying by 1/2 and then adding 3. So these are my final points. What we just graphed above was the vertex form of a quadratic. So we had y equals a times x minus h squared plus k. So that's what we graphed when we did transformations. From this, we call this vertex form because from this we can pull out the vertex. It's hk. And then we also have standard form of a quadratic, which we've been sort of solving and factoring. Y equals ax squared plus bx plus c. So from either form, standard form or vertex form, our a value is the amplitude. So that's the value out in front. The axis of symmetry, we have a vertical line that will be able to draw down the middle of our graph like this. And you can sort of see how if I were to reflect this half of the graph over this line, it would match up perfectly with the other half of the graph. That's what this axis of symmetry is. And you can see it when I just drew in that vertical line, it passed right through my vertex. So our axis of symmetry is always going to be a vertical line, so x equals, and it will pass through the vertex, so it will pass through the h value of my vertex. The max or min value, if we're looking at our example above, again, our minimum value here is going to be referring to the y value of the vertex, right? It's not the x value, because if we think of our domain of a parabola is all real numbers. So there's no maximum value or minimum value for the x's, but for the y's here, they're dipping down until they get to this vertex, and then they're going back up. So the lowest value we have on this parabola is at 3. And for us, that is the k value of the vertex. So the k value for that. Our y-intercept. So a couple different ways we would find that. You would just set x equal to 0 and solve for y. Or if we're looking at standard form, that's really easy to pick out with standard form, because if I plug in 0 for both of these x's, all I'm left with is c. So from standard form, it's 0c. And then to solve for the x-intercepts, we set y equal to 0 and solve. So that's what we just finished up. So we'll either solve by factoring, square roots, or quadratic formula, or completing the square. So if it's in standard form, we'll look to either factor, do quadratic formula, or completing the square. We'll use square roots if we're given vertex form, because if I make y 0, I can just isolate this x minus h squared and then square root both sides. So in the example above, The minimum value, we already talked about that. The lowest value is 3. And what do you think determines if a parabola has a maximum or minimum? Pause the video, think about it for a minute, and then press play to figure it out. So, the thing that determines if it's a maximum or a minimum is going to be the a value. If it's positive, like the example we did above, the parabola opens up. I'm going to come down here and write this down here. If a is positive, the parabola opens up. So we have a minimum value. If a is negative, the parabola opens down. So that k value is going to be our maximum. One little reminder here, an equation is something that's set equal to 0, and a function will be something that's equal to y or f of x. So this is our standard form equation of a quadratic, but this is our standard form function of a quadratic. Now, if we're given a function in standard form, we'll be converting it into vertex form. So today we're going to be doing that by completing the square, and in our next class we'll be doing it by finding h and k. So here we're going to start to convert these into vertex form by completing the square. We're going to do them very similarly to how we solved. So I'm going to start by getting my constant to the other side. This time y is there with that -3. And then same deal as the solving. We either have the choice to factor out my coefficient or divide. I'll show you both ways, but I will tell you when I'm converting, my preference is to factor. So I'm going to do b over 2 squared. So I'm going to add 4 inside the parentheses here. That means I need to multiply that 4 by the coefficient, and that's what I add to the other side. So we get y minus 7 equals negative, and I'm going to factor this trinomial that we just created, x plus 2 squared. And then I isolate y, so I just need to add 7 to both sides. So that's my vertex form. On number 2, I'll show you how to do the division method. So we subtract 13. When you do division, you have to remember that we're not dividing by 12. We're also dividing the y. So we have to do y over 2 minus 13 over 2 equals x squared plus 6x. So that's sort of the tricky part of dividing. We have to remember to also divide the y. And the tricky part about factoring is that you have to remember to multiply what you're adding inside the parentheses by that coefficient to figure out what you're adding to the other side. So both of these have sort of a tricky piece about them, both methods. All right, so we have b over 2 squared, so that's 9. So I add 9 to both sides. I'm going to add 9 as 18 halves to the other side. So we get y over 2 plus 5 halves equals, and I'm going to factor x plus 3 squared, and now I just need to work on getting y by itself. So I'm going to subtract 5 halves from both sides, and then I'll have to multiply both sides by 2. So we get y equals 2 times x plus 3 squared minus 5. So in the next section here, we're solving equations. We just actually converted these two into vertex form as functions. So if you want, you can start with the vertex form instead of the standard form, or you can go straight from standard form. It's up to you. I want you to pause the video and you can press play when you're ready for the answers. Okay, go ahead, check your answers. You can check with my work. Now you want to start to relate, we're going to start relating these to x-intercepts. So this was an equation, so these were solutions here for my equation. But if I had a graph of a function, what would be my x-intercepts? So here, for this one, we end up with imaginary solutions, so we don't get any real solutions to graph, which would create my x-intercepts. So we have no x-intercepts for this one. For the second one, my x-intercepts are exactly as my solutions are because they are real. So we would have -2 plus and minus root 7. And same deal for number 3. We'd have -3 plus and minus root 10 over 2. So these are exact. If I were to actually graph these, I would put these into my calculator to get some approximate answers. Now for the next part of our notes, I want you to sort of take out a highlighter. We're going to walk through these. So this is talking about the discriminant. So discriminants are used to figure out how many real solutions you have or how many x-intercepts you have if it's a function. So what do you notice about your x-intercepts and what you got by solving for x? Basically, what we related our solutions to, when we related our solutions to our x-intercepts, we noticed that when they're imaginary, you don't have any x-intercepts. So the discriminant is basically like the piece underneath the square root from your quadratic formula. So we use to find the number and type of roots for a quadratic equation or the number of x-intercepts for a quadratic function. So you can see for a quadratic equation, it's the type and number of roots or solutions. And for a function, we're looking at the number of x-intercepts. So I have this broken down a little bit. If the value of the discriminant is positive, so if it's an equation and the discriminant is a perfect square, you end up with 2 real rational roots. If the discriminant is not a perfect square, you end up with 2 real irrational roots. So that just means that these ones here will be just normal fractions, rational numbers, like something we could get from a quadratic equation that we factored. This would have some sort of square root in it. But all that means for a function is that it has 2 x-intercepts. So for example, if we're looking at this equation, we end up with a discriminant b squared, so -4 squared, minus 4 times a times c. It tells us we have 2 real irrational roots because we got a positive value that is not a perfect square. However, if it's positive and we have a function, all we're concerned about is the number of x-intercepts. So it's positive, so we have 2 x-intercepts. The next one, if this is exactly equal to 0. If it's exactly equal to 0, we're going to end up with 1 real rational root, and it will be a double root. But for x-intercepts, it just is 1 x-intercept. So if we look at a function over here, an equation x squared minus 8x plus 16, if we do the discriminant, it's -8 squared minus 4 times 1 times 16. We end up with a discriminant of 0 that tells us it's 1 real rational root that we'll get out of this equation. but for the function, if I went to graph this, it would result with just one x-intercept. And then the last one here, if that discriminant is negative, my solutions for my equation will be two complex conjugate roots. But since they're imaginary, complex there, that means for my function we'll have no x-intercepts. So again, here for this equation, b squared minus 4ac will give us a discriminant of negative 24. So if I were to solve this, we'll end up with two complex conjugate roots. And if it's just a function, that just means no x-intercepts. So I'll tell you what I normally use this for. If I have a quadratic and I'm trying to figure out if it's factorable, I'll find the discriminant. And if it's a perfect square, then I know it's factorable. So that is usually how I tell right away if something is factorable. I just find the discriminant, and if I get something like 25, I know it's factorable, so I'll go ahead and factor it. To finish up here, we're going to do a little bit of graphing. On number 1, it's already in vertex form. For 2 and 3, we're using the same functions we just found before. So I'm going to have you pause and go and write those vertex form of those functions down. Okay, we're going to start graphing. In these examples, we're going to state the vertex, axis of symmetry, the max and min value, the y-intercept, and the x-intercepts. And we'll list the x-intercepts exact and approximate. So on number 1, we can see, so the vertex I can pull right out of this. If you're not sure what h is, you can take the inside of the parentheses, set equal to 0, and solve for x. That gives you the h value of your vertex. And then your k value is always what's on the end. So there's my vertex. So I'm going to plot that, 2, 3. And our axis of symmetry is a vertical line, x equals, and it's x equals the h value. So it's going to pass through my vertex there. So next we find the y-intercept. So I'm going to find the y-intercept by plugging in 0 in for x and solving for y. So we get 5. So 0, 5. Now, a nice easy thing that we can do here, because of this axis of symmetry, I can get a symmetric point on the other side of this axis of symmetry just by reflecting this point over my axis of symmetry. So this is 2 units away from my axis of symmetry, so it'll go 2 units in the opposite direction. And so I'll call that my symmetric point. And the coordinates of that symmetric point looks like 4, 5. And now we can see this is a parabola that's opening up, and so it's never going to cross my x-axis. So we can just say no x-intercepts. So don't go through the work of solving that quadratic and finding that it has imaginary solutions and then saying no x-intercepts. Use your graph as a visual to determine if you have to solve or not. And then finally, we have a minimum value, because it's going to be opening up, we'll have a minimum value at 3. So we have a minimum of 3. And I'll connect. On number 2, let me erase some of this highlighter here. On number 2, we have a vertex of -2, 7. So I'm going to plot that. That means my axis of symmetry is x equals h, -2. And I graph that. Next, I'm going to find my y-intercept. Since we have standard form up here, remember my y-intercept is just the c value. So I don't have to do as much solving for my y-intercept as I did for the previous example. So my symmetric point, if I reflect that point over my my axis of symmetry, it's 2 units away. So I go 2 units in the opposite direction. And that gives me a symmetric point, which is -4, 3. So we can see that we have a parabola, it's opening down, we will have x-intercepts. We did find on the on the previous page that the x-intercepts for this were -2 plus and minus √7, 0. So these are the exact ones. That means simplest radical form. Now we want to get approximate ones because I don't know how exactly where to graph for -2 plus √7 or -2 minus √7. So we want to take out our calculator. We'll put this into our calculator and find the decimal values. So -2 plus √7 gives me, we'll round to the hundredth spot, 0.650. And so -2 minus √7 gives me -4.650. So I'll graph here, and -4.65 would be about here. And there's my parabola. This one, because it's opening down, we end up with a maximum value. So the highest point here is 7. So we have a max of 7. Now one last one here. On this one we have a vertex of -3, -5. An axis of symmetry of x equals h, -3. So let me graph that. -3, -5, and axis of symmetry at x equals -3. So we have, again, standard form, so that tells me my y-intercept without having to solve for anything. So 0, 13. So that's going to go off a little bit, but I'll mark way up there. So if I extend out my axis of symmetry a little bit, we have a symmetric point. I'll have to, this y-intercept is 3 units away from that. So if I go 3 units in the opposite direction, that brings me to -6, 13. This is going to be a very skinny parabola. And then I have my x-intercepts, which we already solved for. So my exact x-intercepts, we said they were -3 plus and minus √10/2, 0. And then we just need to plug these into the calculator to get approximate answers. So -3 plus √10/2 gives me -1.420. And -3 minus √10/2 gives me -4.580. So I'm going to graph those as closely as I can. And then I'll connect to make my parabola. So for homework, you can see at the bottom we have some text pages. I want you to graph and label 9, 10, and 12 just like we did these ones above.